Okay, we're gonna get started. I guess I get to be up here. So this is work we did at Bloomberg, and we thought we'd share with the community. It's performance analysis of the different techniques, and while maybe everybody knows this, but the other members of the community may benefit, and we hope that the interaction will benefit us as well. Okay. So the agenda is, I should say our starting point was what some people will call IPUs or DPUs. And that's where we started. We did a phase one where we're just analyzing IPUs or DPUs for host processing and the value they add. That's not the purpose of this presentation. So once you offload some things to the hardware to do per packet processing, essentially, other things start bubbling up on the stack. And I would call that phase two. We ignored the traditional offloads like TSO, etc., and then we saw where the value comes in, and so we decided to measure the different techniques that exist out there for host offloading, for host processing. So that's the agenda. I'm going to show the experiments we did. We experimented with the various transmit zero copy techniques. We even went as far as doing something very basic, like don't turn GSO or GRO on both sides and see what you get. We use that as a baseline. Then we turn on TSO, GRO. I'll go over the experiments after that. And then some of the challenges we faced, we reached out to some of the authors of these techniques, and we even got patches from Pavel. So, lessons learned from XPUs. I hope I can zoom through this real quick because, like I said, it's not the purpose of this presentation. This is how things would look like. So our initial experimentation was, and I know remote people can't see me here, but if I do this, probably they could. Initial presentation, our initial attempt was to work on this part here, which is just a basic match action ASIC, typically on the two vendors at least we tested on. And you offload things that so that the host doesn't have to do these things like firewalling in the appropriate environment, load balancing, layer 4 downwards, right? And when we went past this stage, we saw other issues. I'm not going to go over this. I'm sorry. This is not the purpose of this presentation. But I'm going to provide context and maybe some basic numbers we found. Okay. So next. Trying to find the mouse. Oh, I could do this. So if you we try to break down the infrastructure into several layers, generic. So if you look at the blue, that's you're hitting the socket layer and up. You're dealing at a message level processing. The yellow is what I'll call network infrastructure. You're doing L3, L4. Ethernet, you're doing all this header processing, etc. And there's a device layer, right? So things like TSO, GRO would still be considered as infrastructure. They fit in the boundary between yellow and blue. But anything that's layer 2, layer 4 to 4, like ACLs or load balancing or QoS or just header processing, parsing, etc., that still fits in the yellow. And the red is application. So the end goal is to provide as much RAID as possible and cut down the other ones. This is the historic evolution of where things have been. If you look at the very far left, in the pre-medieval days, when Zen was a thing, I think Zen is still a thing, actually. You have people doing the hypervisors on the host, and then the VMs, and everything is done in at the host level. Then the NICs are sort of infrastructure is kind of moving, and you see some offloads start to happen. Connect X5, probably XGBE days in a small scale. Some of that network infrastructure is now moving into the hardware, and you start slowly to see a lot of movement. And where we are is the last, right? You know, storage, termination, etc. People will just give you like a virtual disk, but you terminate TCP and VME on the NIC, for example, right? I don't want to go into a lot of details, but this is just context. So I'm using color coding just to, so the yellow again is the infrastructure. Once you start offloading on the ingress side, incoming packets, we saw anywhere between, and we tried this, results are with ACLs, where we use actually TC to do this, 10 to 95% improvements on the host CPU, depending on your traffic. For example, I think everybody probably here knows that if you have very large messages on KTLS or TLS, you benefit more from the offload than if you had small messages. So you could get on the anywhere from 10 to 95%, but it's very traffic dependent. On the egress side, it's a lot less, but if you sum it up, you save a lot of CPUs. If your workload requires that. If your workload doesn't require it, then probably doesn't make sense, okay? So again, I should say that there are two patterns. One is, you have a lot of packets per second. Then maybe one technique is you want to reduce the packets per second. So things like TSO, GRO, that's the main trick. The other overhead is per flow overhead. You know, how many flows per second do you achieve? Because every time you get a flow, you have to create state. Every time you terminate, you have to delete the state. So how long and short the flows are is very important and has an effect on offloads. I'm breaking down this based on, so if you remember that diagram I had with yellow at the bottom, blue in the middle, red at the top where your application, our offload, if you're reducing your packets per second, so remember that 64 bytes at 25 gig, unidirectional is 35 million packets per second. So you are doing processing 35 million times a second if you're doing wire rate 64 bytes. So if you can offload that to the hardware, it's a big win. That, whatever that layer of the processing. You increase your MTU, that's a technique. You go down from 35 million to 1.6 million. You go to 4K, it's 500,000. You go to 9K, it's 250K at 25 gig. Multiply that by 4. So achieving 100 gig, the overhead of per packet is not as huge because your packets per second is low. Okay? So lessons learned from that is reduce the packets per second. So what you can see on the left-hand side here is by offloading some of these things, the cost of yellow in the CPU went down. But what happened is the blue starts showing up. The blue is sort of the memory copies, the locks, the transitioning from headers to the socket layer. The application, if all you looked at is the application, you suddenly saw your application getting a lot more CPU cycles, right? So this is the effect of application message sizes. Effect of flow sizes, again, is the same. If you have a very long flow, I think the previous presentation was showing long flows are good. Yes, long flows are good because you amortize the cost of the setup and the teardown. If you have a very short flow and then you open the socket, you sync, arc, 3 packets later, you're shutting down. Not very valuable to, for example, to do any offload other than the traditional checksum or whatever, right? So again, if you have very long flows, you can see on the left-hand side, the yellow goes down on the long flows, but not on the short flows, because you're still, for you to transition to offload, it takes, it's almost not worth it, okay? I don't want to say that, those are very strong words, but it's most advantageous to look at long flows, storage, ML training, file serving, backups, long-lived RPCs. These get a huge cost benefit because they amortize over that period. And so our focus on the experiments is going to just be based on that. CPU time infrastructure, I'm going to skip this because but this is our vision of where we want to go. So you start at the left-hand side, you can see the network. This is what it is today before offload. And by offload, in this case, I want to distinguish between the ACL, the classical L2 to L4 offload of, let's say, TC, or net filter versus the classical host processing. So there are niches out there that care more about one, others, like the big cloud vendors, probably care only about the host side of things, right? So they may have no need for ACLs. But after you offload the ACLs, you see the yellow goes down. The application, which is the most important piece, gets more value out of the CPU cycles. You go to the third one. This is ideal. This is what we're shooting for as our next stage. This actually shows the evolution of where we want to go. You can see the yellow is still up there, but what we're trying to do is to cut the blue. The blue, and this is the essence of what these experiments are. We want to cut down that blue. Hopefully next Netdev, I'll show up with this. We want to totally remove that and put it on the ARM cores on the NIC and just shoot packets straight to the host application, right? Okay, so I'm going to skip the summary of where the value is in offloads, but I think I kind of mentioned it. I went over it in detail, and I'm going to jump to the overcoming the host messaging interface. And I'm very clever. I see the title there, it has blue. It's that blue color. So why is this relevant now? Well, 800 gigabits, I think I had somebody, I think it was Jake, was mentioning in one of the workshops, 800 gigabits, they were testing 800 gigabits, and you have some challenges or some, I don't remember the context, but somebody mentioned 800 gigabits exist. And I have seen talk from Broadcom of 1 to 1.6 terabit port, a single Ethernet port on your host. Now, granted, that's probably machine learning type of traffic or AI, where you're just doing direct DMA to the GPU. So one of the techniques is packet per second reduction techniques. Like I said, if you can go down from 35 million to 250,000 packets per second, your cost per packet is reduced, right? And your PCI bus transactions may not be as affected. Okay. So these are solutions that do not require any application changes. I believe the gentleman before me was suggesting that they like the TX memory zero copy because the changes to the app was very few, as opposed to IO Ring, which has a lot of changes, right? So solutions that don't require any application changes. If I just turn on GRO, if I'm TSO, big TCP, which is the bigger TSO and GRO, I can put GRO with hardware offload. So large payloads with a single, if I can packetize towards the blue with a super packet on the receive side and packetize the other direction as well with one super packet that has a huge message size. So things like that, basic offloads of per packet processing, checksums, which is a favorite in this conference. And we reduce the PPS further by increasing the MTU. If we can go from traditional 1.5K to 4K to at 4K example, we have 2.25 million packets per second. If we use a jumbo frame, we can cut down by half. And tons of, you can handle that in the host, right? The other techniques like cache hit improvements, they improve your cache hits. Interrupt moderation happens to be one, NAPI, and batching of packets either in the transmit or receive path. Okay. I don't want to spend too much time on this, but this is how TSO and GRO. Is there anybody who doesn't know what TSO or GRO here? Or should I just skip that? Raise your hand if you know what GRO is, because they are. Okay, I think I'm going to skip it, okay? But you can look at the slides after. I'm going to use Joe's technique. Look at the slides after. And likewise, the one difference I wanted to point out is probably, because this is still, there's not a lot of NICs that support this, that if you look at the coalescing of GRO, is it happens in the host. But if I go and I do hardware, you can see that the hardware does the coalescing of the segments, and I just received, for example, a 64K payload of the headers on the host, right? So that's a small difference. But eventually, what TCP sees is this super packet with a big segment. Okay, and the big TCP is big because it makes the GRO and GSOs larger, right? So in our experiments, we went with 120K KIB as opposed to the default, which was 64K. And unfortunately, I think I should say now before I forget that we did not change the kernel from 17 segments to 45 segments. It required a kernel, and we just didn't want to mess with the kernel that we had, which was provided to us. But that's one of the things we will go back and do. It would be very nice if there was a config option that I can just tune in and say, go to 45 segments. I know that, I think, Alex, you posted something like some drivers will just go nuts if you just go and change it randomly. We may have seen this, I think, in one of the, I can't remember, it's the I-250, one of them just went crazy, so we just turned it off. We basically undid our change. Okay, so the cons of doing reduced PPS, which is GRO, TSO, make your MTU very large, is, yeah, I think if you like your latency, that's probably not a good thing. And you still need to know how to tweak things, either through ccTL or set your MTU correctly. Got to know that your MSS has to be specific size in order to fit properly on the memory pages. So that's the negative. But if you're doing bulk kind of transfers, it works great. Okay, so data movement techniques. This is, and by that I mean reducing the effect of the memory bandwidth utilization, zero copy essentially. I'm going to use this diagram here. It was, I think, David Way presented this with Pavel last time, but I think I saw it again this morning. But you're basically, by doing zero copy, you're cutting down the amount of copies you do. Therefore, you have less effect on the memory bus. Okay, and if I'm going to show IO-ring, I have to show DevMem as well. This was a slide from Mina, I think, last time. You can also cut the bandwidth this way if you're doing device to device. This is just showing the morning talk on the IoTLB was very appropriate for this, but this was from Netdev 0x17 again by somebody, Rachit, and the Cornell students that presented. Okay. Now I'm going to jump to the second set of all the zero copy techniques require some application change. Some very little, some you really have to rewrite your app essentially, right? I'm just going to quote here that these techniques exist. DPDK and friends already have been doing this for years. They bypass the kernel altogether and you just slot your DMA to a user provided memory. There's a semi-kernel bypass, AFXDP, for example, that we have, which you could optionally ask it to process things through the regular stack or just shoot things to user space. Sendfile has been around for 2,000 years. It's been used for files to sockets. And the other receive message techniques. So RX, as far as is concerned today, the only RX zero copy is the one that Eric put out, where you have to split your headers and make sure your MSS fits on memory pages. The payload goes directly to the application. It's a page flipping technique. For the transmit side, we have a bunch which are, we've got message zero copy and IOU-ring. I should probably mention Sendfile in that breath, but they use page pinning. You basically grab a ref count, and in the case of message zero copy, you release your ref count when you're freeing, and you're grabbing your left. I believe you're grabbing the ref count at live as you're pinning these pages during send message. Am I correct, Willem? No. Yeah, okay, he says it's good. Yes. And with IO ring is a slightly different technique where they grab this ref counts and then you use, am I correct, Pavel? Okay. So there's slightly different philosophies, basically. Okay. The cons on zero copy, because bye-bye KTLS, I guess, or is someone going to disagree with that? You can't do KTLS now. You guess you have to do TLS in user space, or any comments on that? True? Just give me a thumbs up if it's true. But Vadim is here. But you can still do hardware offload. You just can't do KTLS as we know it. Correct? Would that be a fair statement to make? You can, I think you can do TLS. The hardware engine can do TLS, but the other techniques is, you know, if you use, I can remember the Intel approach where they have like something sticking off a PCI bus, which you can do a sideband encrypt, decrypt. Okay, I'll take that offline, but the techniques that dependent on the kernel being the exception path, let's say when you have packet reordering or etc., are no longer applicable because you want to encrypt and decrypt on the payload, and the payload is being zero copy to user space, for example. Past studies, these are the, I think JC back at the OLS 2005 presented a page flipping technique for E1000 driver, if I remember correctly. I don't know if JC is here or not. But the benefit, the win is if it only starts showing benefit, there's an amortization cost of the page flipping. After the smaller the message size, you lose basically, right? It requires non-trivial application changes, and you still have to tweak your kernel. Okay, so now I'm going to go over our experiments with that context. So our setup, our goal is to saturate two links. We did not test the one flow, except one case where we're trying to test the IO ring changes. 16 links, 2 by 100 gig. It's totally IPv6. Very long transactions, like messages are huge. Very long flows. It's streaming basically, as opposed to transactional. And we're basically testing, we're collecting data on the sender and the receiver. The message size we stuck to 512 kilobytes because that looks reasonable. We did some big TCP RR transactions because the data, all the performance numbers we did for big TCP were transaction. We didn't see any streaming tests. So I don't know the reasoning for that, but everybody who does big TCP measurements shows TCP RR. Okay. So the setup looks like this. So it's an Intel IPU, Intel 21000, which is also known as Mount Evans. Directly back to back. So Sapphire Rapids motherboard has a Sapphire Rapids 48 cores, DDR5. The machines are exactly the same. We actually had done earlier scenarios where the machines were different make, and it was a bit tricky to evaluate the results. Right. So with ton of hyperthreading, you have 16 cores, pinned to IRQs, RSS to select your flows, and we pinned the apps on the same one. This is our own application, I should say. I don't know if I mentioned that earlier. It's based on Eric's zero copy self-tests example. We hacked it and we added everything under the sun on it. The test, so it's 200 gig. It's basically 2 by 100, but we are trying to fill the pipes on both links. Header split was always on. Test duration was, we ran it at 100 seconds, repeated 3 times and averaged. So it sort of hides if there's any jitter, then, at 100 seconds, you're doing fine. It will eventually, you get to the steady state. Power was in governor mode. So it starts in governor mode, and then of course we watch the power, and eventually it settles down. So we were good there, and we had an external power measurement tool. So we put this thing outside. It's like a power bar that you can connect and poll for the power utilization. It's not very expensive, but you only can connect 4 things on it. I'm sure that the big players have much more sophisticated equipment than this, but that was a cheap device. Okay, so in case I have to come back to this, that's the Intel driver version that we used, the IDPF driver. You can see the MEM setups we have. The MTU, I guess we varied it from 1.5K to 4K. We didn't go up to higher MTUs. We had some small challenges. At the last minute, we decided to take off the 9K MTU from our results. So that's what it was. If I'm missing anything here, please correct me and just say you forgot to tweak this one thing, right? That's what I'm hoping we get out of this. So we're interested in 3 things. One is throughput. The other one is, because if you just look at throughput and you don't consider how much CPU is being utilized, how much power, you may get the wrong impression that one scheme is better than the other. So we measured everything, and then we computed a methodology which looked at everything and decided what we call as an ROI based on my desire for throughput and how much CPU is consumed, which one performed better, right? So again, like I said, we bound to 16 cores, program, same thing already described, and we use our own homebrewed test program. Okay, so now for the experiments. Okay. As you can run this for days. I mean, our experiments are now automated. They take about a whole day to complete. So the MTUs are varied, 1.5K to 4168, giving us a 4K MSS. Our baseline, as unreasonable as this may sound, was don't turn GRO on the sender or the receiver, no TSO, turn it off. That may sound crazy if your card is capable, at least of TSO. And then we also have software GRO and hardware TSO. The NIC that I described, the Intel NIC, can do 64K hardware GRO basically. And for big TCP, we made it 128K IBs. For hardware GRO and hardware TSO, so we replaced the software GRO with hardware GRO and then see, okay, what difference do I get? And for zero copy on the receive side, the only thing we tested was 4K. I'm pretty sure you can do a lot better with 8K, for example. I could be wrong. On the sender side, we varied again, no GRO, no TSO. Then you turn on GRO, hardware TSO, although it's not as valuable there. We have IOU ring, then IOU ring zero copy. I just want to distinguish between those two. One is the intention, I believe, is to save on syscall, right? The syscalls are cheaper because of the way IO ring handles the batching, etc. Then we tried send file and message zero copy. So if you take that and so this is a matrix. You vary different things on the sender, on the receiver, and then you collect the results. Okay. So I'm going to start by showing just the baseline. The baseline being so here's a 4K MTU, right? We are able to hit about 100, between 180, about 187, let's say, gigabits per second. You don't turn on anything. So this looks impressive. I'm just going to set my MTU to 4K. I'm not going to get 200 gig, but I don't need to change my application, right? And what you're not seeing is that 1.5K is off the chart, is somewhere down there. And then we say, okay, let's turn on GRO and TSO. And in this case, what we have is at the very top here, you see that gives you the best numbers is 4K MTU, zero copy receive, and hardware GRO, right? Does give you the best numbers, because given this is IPv6, the headers are consuming some of that bandwidth. Followed by, this is everything in the alphabet, right? 4K MTU, zero copy receive, hardware GRO. That's the top there. The next is 4K MTU, but just hardware GRO. You're not doing any RX zero copy. And then you go to just plain, sorry, you go to plain 4K MTU versus with zero copy receive, and then just plain 4K MTU. At the blue here, you're seeing 1.5K MTU, so a lot more packets are coming into. However, with hardware GRO turned on, right? So this doesn't tell you the full thing. So next we turn on IOU ring on the transmit side. The variation is not within region of error. There's not much change, as you can see. The next we turn send file on, right? And the send file on the transmit side, not on the receive side. Again, the only thing we're seeing is that the hardware 1.5K hardware GRO is beginning to go up. It's looking better than it did before. And then you turn IOU ring with zero copy. And of course, in all these cases, GRO now, we don't turn off GRO. But you can see that the 1.5K MTU benefiting big time. The 4K MTU also seems to be going up. These other three here, basically zero copy receive, hardware GRO, those are always doing better. But what's interesting is not the 1.5K MTU with just hardware GRO turned on, okay? Then we go message zero copy. And while they look at par, what's interesting is the regular MTU seems to be benefiting as well. But the difference between those two is not huge, right? Kind of very hard to make a decision what to go with. I don't want to change my application. Very clear, you need, just go with the 4K MTU plus just hardware GRO, which is the dark, which is giving you excellent performance, right? So just turning on hardware GRO at 4K MTU, no change to your application, you're winning, essentially. So hardware, it has extreme value, basically. Now, if you look at that, it's not, I'm sorry, don't look, these are kind of difficult to see here, but I didn't want to go and through every single point there. But you can see the benefit, the CPU usage. So now you're looking at it from okay, how much CPU did it cost me? And clearly, everything, including all the hardware GROs are doing really well, right? In terms of, so this is the sender side. I mean, there is an effect. There's a side effect. If you improve the receiver, the sender also improves, right? So as you can see, what we're seeing here is, for example, anything to do, okay, maybe I'll just make some observations that message zero copy was consuming more CPUs, more CPU cycles than IOU ring transmit. The other thing to note is hardware GRO gives you a lot of benefits, even at 1.5K MTU in terms of how much CPU you're using. The throughput may not be going up, but the CPU is going way down. Okay? And on the receiver side, you can see that the number of cores that 1.5K, classical 1.5K uses is huge. Again, hardware GRO, you add zero copy receive, fantastic, right? But even without zero copy receive, hardware GRO is giving you a big win. Okay? So again, if we sum up the CPUs, I'm just going to take all the CPUs. It's probably easier to visualize this from the sender and the receiver, sum them up and show this. And you see that you can very clearly see that. I mean, I'm not even going to touch any of this other stuff here. I'm just going to focus on IOU ring and message zero copy on the sender. And then if I want to really go up, there's competition now between hardware GRO, 4K MTU, versus on the receiver side, versus hardware GRO, 4K MTU plus zero copy receive. That's what you want on that's the contention. So I've shown you a lot of diagrams. It's kind of very hard to visualize, again, what choice, how do I choose, right? So we came up with some, sorry, I'm going to show the power. The one interesting to observe on the sender is that even though if I looked at the CPU if only I looked at the CPU level here, it looks like IOU ring is very good, right? But if I go and I look at the power consumption, well, message zero copy is doing very well. It's consuming less power than IOU ring, right? So there's a lot of data, right? If I look at the total power usage again, you can see clearly that IOU ring is consuming a lot more power than message zero copy, even though it consumed less CPU. So there's some mystery here, right? So it was very hard to sift through this data. We came up with some formula on how do we evaluate these things. So one is to say, I just want to look at it from a throughput perspective and how much CPU I'm consuming. I don't think a PhD student would probably approve of this, but this works for us. You know, you make it, you take your throughput, square it, and then sum up all the CPUs being used and see from a throughput to CPU perspective what the curve looks like. We did the same thing with power, right? I just should have mentioned earlier on that power with zero utilization was about 200 watts. So when I was showing like 700 watts, it means probably about 550 being consumed. So the ROIs, so the higher the number, the better. Again, IO ring looks pretty good on the sender, right? From a CPU perspective. Message zero copy looks pretty good from a power perspective. Okay. Same thing with on the receiver side. I mean, it looks very similar, but if the transmit side is looking different. Now we went to big TCP, and I'm going to just skim through this very quickly and just get to the big arrow, and it's very similar again. I mean, if you look at the power on the sender, I'm sorry, I just focus on those two now, between the transmit being the IO ring versus message zero copy. Clearly, there's a difference. If you look at it entirely from a CPU perspective, there's a difference, right? So at this point, we decided, and now I'm going to say, okay, what's the diff? It's very hard to visualize. If you have so much data, it's much easier if you can find a way to explain it through diagrams or some very simple one picture says 1,000 words, as the saying goes. This is so big TCP, or increasing your GSO and GRO has effect, right? You can see the pinkish color is doing much better than the green, right? So there is value in increasing that. The other thing we measured is the effect on memory bandwidth, which looked a bit weird. So if you look at on the sender side, before zero copies is the purple curve, and on the bottom is the yellow, which is zero copy. Any of the zero copies were doing really well. You're not consuming the memory bandwidth. I'm going to ignore the LLC cache. On the receiver, it's a bit strange that when we used hardware GRO, we saw a little bit more bandwidth being utilized on the memory bus compared to just standard. It looks counterintuitive. Hopefully someone can explain it to us here. But we ran this experiment like 100 times. This looks wrong. Do it again. Get the same results. Okay, so if you look at the 4K MTU, again, very similar behavior. You see that when on the center side, if you're not doing any zero copy, you're killing the bandwidth. And we only have 16 flows. If you look at the transmit side, at the receiver side, again, the gap is not as huge, but again, hardware GRO is consuming more. And because we were able to do receive zero copy in the receive this time, you can see it's almost zero there. Works and challenges. Eric may be able to answer this. So when we turn on hardware GRO, or anybody else, the number of arcs on the wire, because I can understand why is hardware GRO sending less arcs than TCP receives a super packet, regardless of whether the coalescing is done in software or in hardware. But we saw a lot less arcs. It's about 40% less arcs, which explained the consumption, the CPU utilization on the sender side, which went down with hardware. Hardware GRO literally brought down the CPU consumption on the sender. So that's one quirk. And the second one is IO ring. That's when we reached out to Pavel and company, and they sent us 2 patches. The first one was the power. The quirk about the power being so high, even though we're not doing anything, we sort of idle. That patch worked, but it's not in mainline. Is it in mainline already? Yeah. Okay, so the IO weight is not in the mainline. The second one, which is we saw for improving, so this shows you between the patch, before the patch on the left-hand side, what you see is a percentage of how much, where the state is C1 all the way to C6, and then after, right? You can see a huge improvement on the poll column there. For lack of time, I'm just going to jump. This is when we made the message, the application message size is small. If we went, let's say, to 8K, IO ring did not perform well. This patch is in mainline, I believe. This shows the results. The blue was before, and the red is after, and it shows there's an improvement there. Okay, so takeaways. Big MTUs correlates to better metrics. I guess everybody knew that. Hardware GRO is my new favorite feature. I would almost claim I don't want to change my application. I don't want to do zero copy at all, because I'm almost at par with zero copy, right? And we haven't tested it with the 8K. We haven't really tested it. The NIC, the Intel NIC, does 64 kilobytes hardware GRO, but there's probably a future it could do more, which we expect to do more. IO ring notification processing is super. It shaves a lot of CPU cycles, but as we saw, the power battle was not there. We're looking forward to testing both message zero copy. I think the previous presentation, which showed how they improved the notifications for message zero copy. Big TCP, just going to skip so I can end this. We did not test with the 8K MSS. We did not change the 17 segments to 45. The modification, the previous session. IO ring, the RX zero copy requires page pools. I don't remember if this card supports page pools. Anjali, do you know? Do you support page pools on this NIC? Okay, so we may be able to do it sooner than I thought. BZE poll, Joe. IOTLB, that was a fantastic talk earlier. There was a first session today. And with that, I think I'm just going to stop. And if anybody has questions, or if we have time even for questions.
So for me, the interesting takeaway is that in your initial performance slides, there's basically no difference in throughput across all the things you measure. They're all within, I mean, it looked big on your slide, but it's really only about a 5% difference between the best and worst. So that says to me that none of these techniques really significantly affect throughput. In fact, probably other factors in the system when you're actually running it are probably going to outweigh any differences between those choices. So it seems like it all came down to power consumption and CPU utilization.
Yes.
That's really the only places where they differ.
Yeah.
Hi, Jamal.
Sorry,
Tom.
Can you go back to that slide on the cons? I'd like to add a couple.
Which one? The zero copy one?
Like pretty early. No, with the general cons of the offload, maybe.
Sorry, it's a lot of slides here. That one? That? Or you want me? I can go on.
Maybe there was another con.
Yeah.
But anyway, thinking about GRO, GSO, and offloading them. One thing I would point out is those are opportunistic offloads. They don't always work. And I'll give you an example. Anecdote I use early on in YouTube. They were obviously blasting data. That YouTube servers do nothing but read off a disk, and they were pushing data to the client. So they were relying heavily on TSO, and they were super happy with this. But one day, there was an event somewhere downstream on the internet, and all of their congestion windows collapsed. And now, instead of sending 64 kilobytes at a time, they were stuck sending 4 or 8 kilobytes. So what happened was, while they were running in normal mode without any problems, it was great. And they were running at a high CPU utilization, but they were delivering very high throughput. When they had this problem hit and the congestion windows dropped, all of a sudden, basically, they weren't using TSO. So now they shifted the problem. Now they actually had to move the problem into the CPUs. And the problem they had, and I never really understood exactly why, but this went into a downward spiral and somehow it was unrecoverable. So they were actually losing some YouTube servers for a while until they fixed this. So the moral of that story was, yes, use something like GSO and GRO. However, don't provision your systems to rely that they're always being used. Now, I would contrast that when you increase the MTU size, that's not actually opportunistic, right? So if I go from 1.5K MTU to 4 to 8 to 16 to 32, each increment, basically, I'm getting all the value because that's the granularity. So I kind of agree with John about that. Increasing the MTU seems like the easiest solution in that sense. If you can increase your MTU to an arbitrarily large size, potentially you don't even need GRO or GSO. Obviously you can't do that, and you need them. But I think that's one of the things that we need to add. The other one that concerns me a little bit is the limited packet profiles you're doing. So I suspect you're doing TCP, plain TCP. Yeah, that's a good way to phrase it.
Go ahead.
I suspect you're doing plain TCP over IP or IPv6, right? So what about encapsulation? What about extension headers? One of my complaints, and we talked about this, I guess, Tuesday, people doing LRO or the receive side scaling, that requires that the device actually parses packets. If they don't parse the packets that I as a user want, because they decided one set of protocols to support, but I want a different set, then I'm kind of hosed. So I couldn't get any advantages of those offloads. So I agree that we need the offloads, but there's a lot of caveats here that I didn't think you quite covered.
Yeah, I accept that premise. I mean, in our case, the interest here was TCP, just no. Okay, I wouldn't say there's no SACs or whatever TCP options, but not necessarily running on tunnels. But point taken. Sorry, Anjali, you wanted to say?
Yeah, I just want to add to Tom. So he said if there is some tunnels and you can't really, the hardware doesn't understand the protocol, so you can't really, do things for GRO to take effect or whatever other offloads to take effect. That's why you have a programmable pipeline in the hardware, and that's why we want people.
Okay. I'm going to say thank you, Anjali. Thank you for the plug.
But there was one more. Yeah, I mean, there is certain things to be said. When you pull certain things in hardware, there are more things that get pulled in the hardware. Okay, so that is a con for sure, right? You want to use GRO, you have tunnels, you have to do the decap in the hardware. A lot of hardware will not do the GRO with your tunnels on or whatever, right? Those are some of the cons. The other thing about, I think there was first one that you said, opportunistic, right? So I don't know if you did it. I mean, there is something called flow pacing in hardware. So whenever the shit hits, you're still in hardware, you are able to pace them, so you can still do your TSOs and stuff like that.
We'll give a chance to Parav. Unless you really have to respond, Tom.
So just one other comment.
Okay.
What I would love to see, and this may have been done. So we put all this effort into TLS offload. I think that's going to be the poster child. When you have no packet loss in a pristine lab, I bet you get ridiculously high data rates.
True.
Put a 1 or 2% packet loss in, I'd love to see what happens to that. Because if you have to go back to the host, do resynchronization of your data stream, and you do that a lot, I suspect at some point you wish you didn't even have the offload at all. So that would be interesting too. So I think it's obviously a long story, but we're going to have to open up the field a little bit and look at more problems, more combinations, more basically, as you say, when the shit hits the fan, that's going to determine whether or not offloads are really going to be successful.
I would say that when the shit hits the fan affects other things like NVMe offloads, TCP NVMe. It's not just specific to this problem, right? Anyway, Parav, let's have Parav.
I want to add to Tom. There is a knob in the TCP stack. I don't remember the name, but I'll find out later. There is a watermark that you can set. If you hit minimum these many bytes of TCP, only then do LSO. And that helped us when the connection count was too huge. The TCP stack was still trying to do LSO, a very low value, and the NIC didn't work well for us. So we increased that value. And then there was enough coalescing done from the TCP. We kind of get back the same performance.
Adaptive, good, yeah.
But yes, it's again opportunistic, but there are few tweaks that's possible to do.
Yeah, it's the edge conditions that always get us, right?
Yeah.
When we fall in, especially when it's an unexpected edge condition, that's when things really go.
Jamal, I had a question on your last slide.
Okay.
Or comment. The big TCP with zero copy, I think it's still possible with 17 segments because many zero copy case, it's usually 4 or 5 SGEs and not per page SGE. So you can still send 64K with 4 SGEs or 5.
Yeah, I don't know. I mean, I was gonna talk to Eric about it, but it's I would have preferred to go 45 segments because that's all the tests are using 45 segments to just compare. But
yeah, in reality,
you don't think there's any problem with 64K with 128 kilobytes, for example?
it can work with smaller without the kernel.
All right, thanks.
The first small question is last one is why did you choose the 16 flows? Usually one connection reaches 30 and 8 should be enough. Maybe.
It was, we just wanted to pin to multiple CPUs to see how they're going to be utilized. And sometimes the RSS played games against us, but one flow would have been easier. Yeah.
So there's 2 points I had in response to your talk. The first is when you said one of the cons for some of these features is that you have to then change your application.
Yes.
Seems like you're also kind of indirectly making an argument for it'd be nice if there was some sort of, if you have like RPC traffic, there's some sort of like open source mechanism that, does RPCs that supports these kind of features so that you as the user would not have to care about it.
Mm-hmm.
It'd be nice if you could just have something like, if you have like, I don't know, Thrift or gRPC or whatever RPC library is kind of out there and you can download and use it for your application if it supports the features. And if you only have to change it kind of there underlying, then maybe as the application, you're fine.
So now people love their socket APIs. So I don't know if you want to implement something else, then you'll have to get the religious people to agree as well.
And the second thought is for increasing the MTU size, that sure would be great for large applications. If you have like a mixed workload where you're also getting a lot of small traffic, small RPCs in, it seems like there might be the potential for memory consumption being an issue. If you have 4K MTU, you've populated your ring buffers with pages, but maybe every RPC you're getting in for half your connections on the system are only using a few hundred bytes. Seems like there's this blow up factor basically associated with this. So that seems like the other potential downside.
Yeah, then you consume more memory. You may, and as the number of flows goes up, then you even need more trouble. But this scenario is maybe 1,000 flows is the max good number, and you have a lot of RAM. That machine I should have mentioned, we had, I think, 256 gig or something like that. Thanks. Sorry, John, I should all your time. Thanks.